All right, so in this problem we have a man. He's standing along the shoreline and he's throwing a tennis ball into the water for his dog to retrieve. The dog can run 15 feet per second on sand and swim 3 feet per second. If the ball is 30 feet down the coast and 20 feet off the coast, determine the fastest route for the dog to retrieve the ball. This question is obviously very important because if you were a dog, you wouldn't just waste time going through the water. You would probably calculate what the optimal path to the ball would be. So here we have the guy. He's throwing the ball. The ball ends up in here. And actually, let's make the shoreline here. Okay? So this may not be drawn exactly to scale, but the path horizontally is 30 feet and vertically is going to be 20 feet. And what your dog might do is just go straight through the water because he's not that smart. My dog is going to figure out what the fastest path is to get there, and he's not going to waste too much time calculating it because he wants to get that ball quick. But so you can sort of think of what two extreme paths would be. One extreme path would be the dog goes 30 feet horizontally and 20 feet in that direction vertically and swimming into the water. And you could think of, well, let's think of how long that would be. Well, this would be, he's going to go 30 feet at 15 feet per second. So that would be 30 divided by 15 plus, and then he's going to go 20 feet at 3 feet per second. So if he goes that kind of extreme path, that's going to be 2 plus 6 and 2/3, which is what, 8 and 2/3 seconds. That's pretty quick. But there may be a quicker way. Another extreme path for him to do would be to just go straight into the water and towards the ball. And if he were going to do it that way, what would it be? It would be like, well, you'd have to use Pythagorean theorem, right? So 30 squared plus 20 squared is equal to 1300, and I actually need the square root of all that. So 36, it's going to be 36 feet. And so if he just went swimming the whole time, it would be 36 divided by 3, which is 12 seconds. All right, so those are kind of the two like extreme cases, but the dog doesn't have to go all sand or all water. What the dog may decide to do is just pick a point, get close to it, and run along the beach in the sand that way, and then cut in there. And I think this is where we can turn this into a function and we can optimize it. So I'm going to call this distance right here x. And so then this first leg that he runs is 30 minus x. And if I'm thinking of time as a function of x, then this would be 30 minus x divided by how long it takes him to run on sand, which is 15 feet per second. And then plus however long it takes him to swim in the water. And so this distance right here is going to be the square root of 20 squared plus x squared. So now I'm going to get the square root of 20 squared plus x squared divided by how long it takes him to swim. And so if it, like say if he was going to go 15 feet in the water, it would be 15 divided by 3, which is 5 seconds. It's going to be whatever the distance is in the water divided by 3. And now we have a function that we can just plug into Desmos. And this is where it's kind of going to be helpful to figure out what the relevant, reasonable physical constraints are on the x value. So the x is a number that represents how far the dog runs down the beach, and the beach is 30 feet. So the shortest distance that x could really be is going to be 0. And the longest it could be really is 30. And I think both of those extreme cases that we evaluated before were when x was 0 and when it was 30. And I think we got numbers in between 8 and 12. So let's see if we go to 15 what it looks like. Yeah, that looks like a pretty good graph here. What I'm looking for is the minimum. And in this case, it looks like the minimum is 4.082. And actually, we could put the points 0, comma, 0, comma, f of 0. So clearly the shortest time is at 4.082. And if this were an optimization problem on like an AP exam in calculus, a lot of times you would have to check the boundaries. So you could kind of think of this as if he runs 0 feet, let's see, if he swims 0 feet, then the time is 8.667 seconds. If he swims 4.082 feet, then the time will be 8.532 seconds. And if he swims 30 feet, then the time will be 12.019 seconds. So the optimal path was going to be that middle one right there.